In this video, I'm going to give a brief introduction to the quarks in the Standard Model. So these are fermions. They're all spin 1/2. And one way to distinguish, so when we think of our fermions, we have our quarks and our leptons. The quarks are the fermions which are colored under the strong force. So they interact with the strong force, which the strong force is propagated by gluons. So they're going to interact with gluons. Leptons do not interact with gluons. So that's one of our good ways we can distinguish them. So you maybe haven't heard about quarks before, depending on how much you've studied particle physics in the past. You certainly probably didn't hear about quarks in your high school chemistry class, or at least you didn't know you were learning about quarks. Instead, you probably learned about protons and neutrons. So you learned an atom has protons and neutrons in its nucleus, and then electrons orbit around them. And when we first understood this model of an atom, scientists thought that protons and neutrons were fundamental particles. So we now know that protons and neutrons actually are not fundamental, and instead they're made up of quarks. So the proton we see in this diagram here is made up of 2 up quarks and a down quark, and then a neutron is made up of 1 up quark and 2 down quarks. And so these particles, which we might have thought of as fundamental, actually aren't. We now know that they're made up of quarks instead. And so we have 6 quarks or more, depending on how you count, but we'll start by thinking that there are 6 quarks. They're shown here on the right. So we have 3 generations. Our first generation is made up of an up quark and a down quark. So notice, these 2 particles have some masses. The up quark has 2/3 of the fundamental charge, and the down quark has negative 1/3 of the fundamental charge. So if you go back to look at our proton and our neutron, you notice the proton is 2 ups and a down. That's 2/3 plus 2/3 minus 1/3, which is equal to 1. Right? If you do some fractions real quick. The neutron is 1 up, which is 2/3 of a charge, and then 2 minus 1/3. So 2/3 minus 1/3 minus 1/3. So that's neutral. This fact that we have these 3 quarks combining to make an integer charge is not unique to the proton and the neutron. So part of why the charge of the proton was often referred to as the fundamental charge is because for a long time, scientists thought that you couldn't have a particle with a charge less than the fundamental charge. So we thought there was no fractional charge. We now know these quarks do have fractional charge, except they're always going to hang out together. We're never going to see quarks in isolation. They're connected by the strong force, and that strong force is real strong. So they're always going to come in groups, and those groups are always going to add up to some integer number of that fundamental charge. And so, what we actually see in nature are always going to be composite particles made up of particles which add to an integer of that fundamental charge. We'll learn more about that when we talk about hadrons, so baryons and mesons in a future video. But for now, the proton has charge 1 because of the way the charges of the quarks add up. Okay, so our proton and neutron are made up of this first generation quarks only, up quarks and down quarks. Now again, just like with the leptons, each generation is going to have particles which are getting more massive, but otherwise their characteristics are staying the same. So if we go next over to our charm and our strange, you'll notice the charm is more massive than the up, the strange is more massive than the down, but the charm has charge 2/3, just like the up does. It has spin 1/2, just like the up does. The strange has charge minus 1/3, just like the down does. And it has spin 1/2. All of our fermions we know about have spin 1/2. And then we can go to our third generation, which is made up of the top and the bottom. Again, the top is even heavier than the charm. The bottom is even heavier than the strange. but their charge and spin characteristics stay the same. And so we're starting to see sort of some logic behind these generations that we have. So again, also like the leptons, right? There's this idea that particles which are more massive are always going to want to tend to decay into lighter particles, unless if there's a conservation law that says that they cannot. So again, protons and neutrons are these very common particles, right? We're all made up of atoms and protons and neutrons, which are made up of only the ups and down quarks. And we're already starting to understand this a little bit better, because the ups and downs, because they're the smallest of the quarks, they're our most stable they're stable particles, right? Charms and stranges are always going to decay downward. The top and the bottom, since they're even more massive, they're going to have even shorter lifetimes, and they're going to want to decay even more quickly. Okay, so I mentioned briefly at the beginning of this video that there are 6 quarks, but it sort of depends on how you count. So we already know one of the reasons for that, which is that we know we actually have 6 more quarks, which are anti-quarks. So we have the anti-up, anti-charm, etc. But there's even more quarks. So we can look at this other picture of the standard model, which has sort of all the fundamental particles. So it has more particles. And you'll notice if you look at the quarks, so we see there's the up, and there's a U and a U bar. So often antiparticles are denoted by putting a bar over the top. So the U bar is telling us it's an anti-up. But notice there's sort of 6 ups in there. There's a U bar that's red and sort of blue, and there's a green U and sort of a pink U bar, a blue U, a yellow U bar. So what are all of these different up particles? Well, quarks are colored. And so color is something that is sort of like an electric charge. It's a property of the particle. So there is an up particle, which is red. Now, the fact that the up particle is red does not mean it looks red in any way. It's just what we call it. So it doesn't actually mean these particles have some color in the visible light spectrum associated with them. It's just a name. So we say the up has a property of being red, even though that has nothing to do with the visible spectrum of light. So we have a red up, a green up, and a blue up. And so really, even before we talk about antiparticles, we actually have 3 different ups, which are really different particles. They have all of the same properties that are listed on our previous chart. So the red up, so again, we have the red, green, and blue ups that we see here. They all have the same property as this up on our chart here. They have the same mass, they have the same charge, they have the same spin, and the only difference is their color. So that's why often when we look at the standard model, we just see these 6, because sort of in terms of the values in the boxes, they aren't going to change. So it makes for a much bigger, more complicated diagram to include all of them. But this, since it doesn't include those values, this still looks pretty small. So we have these 3 different types of ups, and then these 3 anti-ups that it's said to have anti-red, anti-green, and anti-blue color. And that's going to be true for all of our quarks. So really, there are 6 down quarks, or you might say 3 downs and 3 anti-downs is probably more precise language, right? So we have a red down, a green down, a blue down, and then we have the 3 anti-downs as well. And so in some senses, we have a lot more quarks than you would otherwise think. So 6 times 6, right? So 36 quarks. So a lot of quarks, actually, when you include all of the different colors and the anti-quarks. All right, so that's most of what I want to say about quarks. We'll learn that before we understood that there were quarks, we were discovering sort of a zoo of different types of particles. And eventually we understood that all of these particles that we thought were different fundamental particles are actually composite particles, mostly made up of different combinations of quarks. So we're saying there's tons of quarks here. And so there's tons of different combinations of quarks. that we could add together to make heavier particles. And that's the next thing that we'll learn about when we learn about hadrons.